let's get started. Today will be the first of 2 lectures on deep learning. The slides are made by my PhD student Joe Marino, so you'll see that they are much prettier than mine. And so today, in the first part, we'll talk about a basic introduction to deep learning, and then in the second part, on next Tuesday, we'll be talking about some more advanced deep neural architectures, such as convolutional neural nets and recurrent neural nets. So first, let's start off with introduction and motivation. So this is just be a little bit of a repeat from what we've seen in class so far, using some of the way Joe likes to present things. So you'll just see a slightly different variation of presenting the same information, which I think is still a valuable experience. So we have data and labels. If y is continuous, like we do regression, then we want to learn a regression function. If y is binary and categorical, like 0 or 1, then we want to learn this, in this case, a logistic regression function to categorize into 0 or 1. That's called classification. Classification, you want to split in the binary case, you want to find a hyperplane that splits the data between one class and the other class, in this case 0 or 1. For the most part, in deep learning, people use logistic regression, so minimizing log loss, or also known as binary cross entropy. So here's just another way of writing log loss. They're all mathematically equivalent. And you minimize binary cross entropy on the training data, also known as log loss, to find the optimal WMV. This is for the linear case. And we solve using gradient descent. So just a recap of things that we've seen so far. So if we want to do something nonlinear, so we saw decision trees and things that build on top of decision trees for the last 2 lectures. But if we want to, in general, learn a nonlinear decision function, how do we do that? Option 1 is to use a nonlinear term. This is something that was actually very common until deep learning became usable. And the idea is that we simply map our original features. Where's my mouse? Where my mouse is. Okay, well you can see here, you can map the original features, x1, x2, to this new feature space that has 6 dimensions. And actually the coordinates of this feature space are actually nonlinear transformations of the original features. So if we learn a linear function in this expanded feature space of 5 features, then we're actually able to learn a quadratic function in the original feature space. We're just doing polynomial coefficient fitting. So that was actually fairly popular. The other option, which is what is the premise of deep learning, is we learn multiple linear decision boundaries, and then we figure out a way to compose these linear decision boundaries. So in this case, maybe we can learn these 2 linear decision boundaries, each of which is okay but not great, and then we find another way of recombining these 2 linear functions. And that, in the essence, is what deep learning does, and we'll get to that. Both cases transform the data into a representation that is linearly separable. Okay, so to think about this in a little bit more concretely, and we're just going to warm up slowly to full-fledged deep learning, we'll think about things that look like Boolean operators, or at least decision functions that look like Boolean operators. So we have an AND operator and an OR operator on x1 and x2. So the first example says both x1 and x2 have to be large. Let's say x1 and x2, both x1 and x2 have that value 1, and then I'll classify as 1, otherwise I'll classify as 0. The second boundary is mathematically equivalent to saying both x1 and x2, either x1 or x2 have to be large, and then I'll classify as a positive class, otherwise I classify as a negative class. Okay, so the AND and OR operators are linearly separable. In other words, if I were to put the AND and OR operators embedded into some sort of feature space, then I could learn this linear classifier that has the same behavior as an AND and OR operator. Okay, so what about XOR? So in XOR, it's 1 if only one of x1 and x2 is 1, and it's 0 if both of x1 and x2 are 1 or both of x1 and x2 are 0. So that's the XOR. Who ever seen XOR before? Okay, so most of the class. Okay. So this is the XOR operator, and I'm just going to embed its logical implications into this feature space. So x1 and x2 both take values either 0 or 1, and the classification is 0 or 1 based off the values of x1 and x2. Okay, neither the AND or the OR operator can model this accurately. And the XOR is not linearly separable, but you can linearly separate it as a function of the AND and OR operators. So if you had two base operators that are just AND and OR operators on the data, and then you learn another function that's a function of the output of the AND and OR operators, then you can actually perfectly classify this data. So in other words, if we somehow were able to transform this data into the output of its AND and OR operators, then the function is linearly separable. Then the data is linearly separable in that transform space. So, in other words, how do we build XOR from AND and OR gates? Here's one way to do this. So we have a composable function. So each of the functions in the first two layers, in the first layer, so the AND and ORs are linear functions. And then we do a negation of the AND function, and then we compose these two, and we make a prediction. So we do an AND of not AND and OR. And this is the function that is actually XOR. So if you actually write out the Boolean circuit for XOR, that's what it looks like. Now we're going to do an analogy to a continuous space. So this is all discrete logic space. We're going to do an analogy to the continuous space, but you can see how this kind of composition allows us to get an operation that's very nonlinear as a composition of two linear functions. Any questions so far? Okay, so to fit complicated data, we need to move towards expressive nonlinear functions. And we can form these nonlinear functions by composing them as combinations of linear. We can form these nonlinear functions by doing compositions of linear functions, and this process can be applied recursively, and that is essentially what deep learning is. And the depth of a deep neural network is the number of stages of this processing, of this recursive processing, or compositional processing. So deep learning, in a nutshell, is learning these functions with multiple stages of processing. Okay. So, one question one might ask is, why not just do this feature lifting, right? So we re-parameterize our representation into this, in this simple case, a 5-dimensional space, where a linear function in this 5-dimensional space corresponds to a quadratic function in the original space. Well, you can, but it turns out that this is a paradigm that is difficult to scale up. Whereas, with deep learning, with enough of these different stages of processings of compositions of linear boundaries, we can approximate any nonlinear function. And this turns out to be a very powerful paradigm that has many benefits, both computationally, in its representational power, and its ease of use with things like GPUs. So there's a confluence of many factors that makes this composition of many stages of linear functions somehow the most effective way to do this nonlinear learning. And that'll become clear by the end of this lecture. Okay, so that was just a preface to build some intuition. And now let's talk about what actually a deep neural net does. So, as we've seen briefly in lecture, I believe lecture 2 or lecture 3, a deep neural net is a composition of a bunch of what are called neurons, an artificial neuron, not to be, at some level, having some relationship with a biological neuron. And this is what an artificial neuron does. It's pretty straightforward. You have your input features, you have some weights, and then you sum those weights. That's just the same as a dot product. And then you pass that dot product through some sort of nonlinearity, like a sigmoid function or some other nonlinearity, and then you get your output. That's what an artificial neuron is. It's just a linear model with a monotonic nonlinear transformation at the end. So we have a bunch of these neurons, so each one with a different set of weights, and you pass those through a nonlinearity and you get your output. And so multiple neurons form a layer. And so what this does is each neuron processes the raw input features and outputs something. And then the next layer takes as input the outputs of the previous layer. So the input features, if you will, the transformed feature space of the next layer is the outputs of the previous layer. And that's a deep neural network. So this is how we do this compositional processing of linear functions. So mathematically, it looks like this. So we've all seen this before. We have this bias term. Oh, I should mention that here Joe's using a notation that's mathematically equivalent, but I just want to mention he uses in Joe's notation he uses a 1 as a feature. He uses a constant 1 as an input to the sum, and then that weight corresponding to that constant feature 1 is called W naught, which in the notation I used previously is the same as the B term. So you'll see this type of notation as well at different places. But it's mathematically the same. And the nonlinearity is typically referred to as sigma. You can also represent this in matrix vector multiplication form. So, the input features and the weights form this vector dot product, and we get this sum. And then we apply nonlinearity. So the sum is a scalar. We'll apply this nonlinear on the scalar. We get a scalar out. One reason why this vector multiplication viewpoint is attractive is that it's easy to write out the matrix form. So if we had an entire layer, then we say we have this weight matrix W, where each column of capital W are the weights of a single neuron. So we can actually do we can actually do a matrix vector multiply to compute the sums of all the neurons in a layer simultaneously, and then we apply this nonlinearity component-wise to get the outputs of the hidden layer. In matrix vector multiplication form, it basically means that we get this matrix of weights, so I guess, and then we multiply on the input features to get us vector of the sums. We apply this nonlinearity element-wise to this vector of sums to get the outputs of this entire layer of neurons. And this is actually what gets implemented in GPUs, for example. Okay. So, a deep neural network is a sequence of parallelized weight sums and nonlinearity operators. So define x, the 0th layer, as the raw inputs. So x superscript 0 is the 0th layer. So it's just the raw inputs. The first layer is the first layer of the hidden unit outputs from the first layer. And we repeatedly apply this operation where we have, of course, different weights at each layer, but we just repeatedly apply the same operation over and over again until we get to the final output layer. Okay. And of course, you could write this in this matrix vector multiplication form with something that looks like this. So this is also a common way that people write out a neural net, at least in terms of describing its architecture. This particular architecture is the most simplest form. It's called a fully connected feed-forward neural net. We'll talk about the other neural architectures in lecture on Tuesday. Yes, question?
I understand conceptually why, like for a neuron, you multiply or not, so it becomes linear. But what happens if you were to just have a linear function beyond that?
Okay, so what happens if sigma was identity, for example? Okay, if sigma was identity, everything collapses to a linear model. So the representational power of a neural net collapses to the same as just a standard linear model. If you don't have the nonlinearities, and you just apply the associative rule, right? You apply the associative rule. Excuse me. This becomes a vector, right? And then this is an identity function. Matrix times a vector is a vector. Identity function, matrix times a vector. Yes, question?
What exactly do you mean by parallelizing?
So modern processors like GPUs and even your CPUs can actually solve all of these operations in one go. If you're interested more, I'm sure they teach these things in some EE class. Sorry, I don't know which number. But modern processors can do this entire matrix vector multiply in basically one go. So for example, if they're not parallelized, then what you need to do is you need to like run a double for loop, or maybe a triple loop. You might need to run a double for loop to do this matrix and vector multiply. And so the amount of time it takes to run that double for loop is equal to the dimensions of the matrix. But if it's parallelized, then you can just do that in one go.
Okay, but sequentially, like that inner product between the matrix and the vector always has to go first before you.
Right. Yes. So sequentially, you have to do it layer-wise. Yes, that's correct. But each layer can be parallelized.
Okay.
So Moore's law, in terms of there's many versions of Moore's law, but in terms of processor speed, they're not getting faster. In terms of how much computation you can pack into a single processor, how many cores, that's still growing. So there's benefits into parallelizing these types of computations, or making these computations parallelizable. And again, if you're interested in details, I'm sure there's the EE class that goes into it. Okay, so just to recap, we now have at least a modeling language or a paradigm for building expressive nonlinear functions. And deep neural networks are indeed universal function approximators. Of course, you need enough layers and units, right? So in the limit of infinite depth and or infinite width, these deep neural nets can approximate any function arbitrarily closely. So for any function f over and some pre-specified input domain of x, in the limit of infinite depth and or infinite width, for any error tolerance epsilon, there exists a neural net that is at most epsilon away from that function over the entire domain. That's the standard type of definition of a function approximation. Okay, so I'm going to do a little bit of reinterpretation. And the reason why I'm going to do this reinterpretation is to convey to you that what a deep neural net is doing internally is applying a series of transformations of the data. So it's learning new representations of the data, if you will. So an artificial neural net, a single artificial neuron defines a hyperplane. This is something that I think should be second nature to us now at this point. And so the output, before we apply the nonlinear transformation, just the raw output of the sum is the unnormalized sign distance of that point to this hyperplane. Okay? And now, when we apply this nonlinearity, we do a nonlinear transformation of this signed distance. So we stretch parts of it, or we compress other parts of it. So in other words, we have this point distance to sign distance to this hyperplane, and this is the original distance. When you apply this nonlinearity, we stretch. It's a monotonic transformation, but because it's nonlinear, it stretches or compresses this distance in different ways, and that's what we get out of an artificial neuron. This is actually a very crucial concept. If there are any questions, perhaps ask them. Yes?
So is the main concept just like you can stretch or compress that distance to any way such that like later on your data set could be linearly separable?
Correct. That's right. Yeah. Yes?
Isn't this limiting yourself to activating functions that are kind of like monotonic?
Correct. They have to be monotonic. Of course, the weights can be positive or negative. It's a monotonic transformation of the output of the sum. And the weights themselves can be negative.
So no one like ever uses a non-monotonic activating function?
I'm sure some crazy person at some point has used a non-monotonic activation function. They are not very popular. I don't know of any in this. I don't know. All the standard ones are monotonic. No one is a very strong. What is it? For all there is, you know, I can't say that. Certainly. But all the standard ones are monotonic. Yeah. Okay. So, what does that mean? That means any individual neuron, you know, is the output of that neuron can be interpreted as a feature, right? Because we're stacking these. So the output of that neuron can be interpreted as a feature. And what does these features mean? That means, you know, the points tend to be over here. It's a feature that's positive if the points tend to be over here, generally speaking, and it's negative, the points tend to be over there, generally speaking. So, you know, it helps you select for these abstract features of points. So, you know, if you have multiple neurons that are multiple hyperplanes, and they all have the same feature coordinate in these neurons, so in the neuron level, at this hidden layer level, they all tend to have the same coordinates. That means all the neurons activate the same way for these points. That means they tend to be clustered together as calculated by these bunch of hyperplanes. In other words, we have this data, right? We have this original data, and we have a bunch of neurons that are these hyperplanes in that data. And now we have a new data set. So each axis of this data set, each axis of this data set is the output of a neuron of the previous representation. So and now we learned 3 more neurons. So this is a layer of, sorry, I should be a little more clear. So the data is 3-dimensional. The hidden layer has 3 neurons, just for ease of visualization. And what I'm visualizing in the top left are the separating hyperplanes of those 3 neurons. And in the middle, again, it's a 3-dimensional representation, which is the outputs, and each axis is the output signal of those 3 neurons in the previous layer. And then we learn 3 more neurons whose input are the outputs of the 3 previous neurons. And then we get a representation that looks like this. And now we learn just a single neuron that's just a classifier, a linear classifier in this space. Question, yes?
Does each neuron correspond to each plane?
In this simple example, yes. So we're only learning, so the data is 3-dimensional, and each layer, except for the final layer, only has 3 neurons, which means the output is a 3-dimensional space.
Okay, and what do the purple and the...
They're the 2 different classes.
Okay, so in the first graph, I understand, but the second graph is also just the 2 classes.
Yeah, they're just the 2 classes. The point, so each point in the first graph corresponds to a point in the middle graph. And the coordinate system is the outputs of the 3 neurons that processed from the first graph to the second graph.
Okay, so the coordinates in the second graph are the outputs
of the neurons processed on the first graph. And of course, this is just 3-dimensional because that's what we can visualize. In practice, you know, X has an image, and the neuron, there's thousands of neurons, but this is the basic idea. Question, yes?
And the same set of labels is used for every neuron?
Yeah, the labels are the same.
Okay.
Yeah. Yes, question.
Why are there 4 planes?
Only visualizing, no, wait, hold on. Only visualizing 3 out of the planes, sorry. Sorry, there are more, sorry. My apologies. There can be, in practice, there are many, many, many planes, and I'm just visualizing, in this case, just 3 of them. Yeah. Yes?
So I'm still trying to figure out what's the coordinate system in the middle graph?
It's the outputs, well, it's 3 of the outputs of the neurons used to process from the left graph to the middle graph. So in other words, let's see here. X superscript 0 are the raw inputs. So that's the coordinate system used in the first plot. X superscript 1 is a set of neurons processed on the raw inputs with a nonlinearity. And let's say for the sake of argument, this is three-dimensional. There are 3 neurons. Then that's what's happening here. That's this visualization. Yeah. Yes?
The dimensionality of the space is variable.
Yeah, so that's part of the design of the architecture of the deep neural net. How many the size of each hidden layer, how many hidden layers. So at each stage, each artificial neuron cuts up its input space with each layer has a layer of artificial neurons, and each one corresponds to a hyperplane in this input space. And the input space is defined by the outputs of the previous hidden layer, the previous layer. And we cut up the space in these hyperplanes. We evaluate the distance of the point to each hyperplane. We transform these distances with a nonlinearity function. So we stretch or compress that distance function with this monotonic transform. And then the transformed distances become the points in this new transformed space. And we continue. We continue until the data is sufficiently linearized. Okay, big picture. Neural nets are function approximators. They have this nested structure that keeps composing and composing that allows them to capture a broad set of functions. So, one way to look at this. And can approximate a variety of functions, in particular, conditional probability distributions. That's the most common use case these days in practice. If you have some categorical data, you want to compute the probability of it being class 1 versus class 0, same as logistic regression. So, and you minimize, let's say, binary cross entropy or multi-class cross entropy. And so the top layer of the neural net, the top layer of a neural net is typically just a logistic regression in practice. Sorry. Any questions? I haven't talked about learning yet, which I will next, but any questions so far? Yes?
I feel a little sketched out about the idea that how you said that a deep learning algorithm can make any data set linearly separable. But I guess I'm trying to.
Oh, that's not. Well. Okay, sorry. Finish your question.
Yeah, I'm thinking of just extreme examples. Say you were trying to predict someone if they have cancer, and you just recorded their height and weight. And of course, there's not going to be a strong correlation with this data set. Would you just if you really wanted to make that linearly separable, would you just need literal infinite amount of data, infinite amount of time for training, and just that would very incrementally increase accuracy over time?
So that's a great question. Neural nets are not magic.
Yeah.
Right. So if you have some high-dimensional space, data space, which means you measure many variables, not just 2, and there exists some curve in this space that separates the data with high accuracy, then with sufficient number of transformations, you can find a linear transformation of that. You can find a linear representation of that space, at which then the final layer is just a logistic regression model. But it's certainly true that if your initial measurements, are not expressive enough, then you can't actually get a high accuracy. Okay. But certainly, the thing that really caused neural nets to be popular was in about 2011, 2012. Deep neural nets won the ImageNet classification challenge by a wide margin. And we can all look at an image and say, oh, that's a cat, that's a dog. So there must be some transformation of the data that enables the classifier to do that. Okay. now I'm going to talk about the learning algorithm, which in the deep learning community and neural net community is commonly referred to as backpropagation. But it's really just gradient descent. Okay, so what I talked about up to now is that neural nets are universal function approximators in the sense that for this class of neural nets, there exists some configuration of it which can learn this function, in which case it's a function that has high accuracy on this data. How do we find this function? How do we learn the weights of a neural net to achieve high accuracy on this data set? So this is the space of all neural nets of a certain class. We want to find the one that minimizes loss on a training set. And we do so by adjusting the weights. So this is just a different way of looking at some of the stuff we talked about over the first few weeks. We have some loss function, and we have at each point in this loss function, and this is a one-dimensional projection of a weight parameter of it, and how it's setting that particular weight while holding other weights constant will cause the loss to change. And we do it via, for a single weight parameter, the directional derivative of the loss with respect to that weight. If we do it for all the weights simultaneously, that's called the gradient. And then we do gradient descent. So nothing new here. The same thing we've talked about in the first 3 or 4 lectures. Backpropagation is just another way of saying gradient descent in composable functions. So a deep neural net is basically a composable stack of functions. And so backpropagation is just the word they use to talk about gradient descent through this composition. Okay. And in other words, it's the chain rule. So here's a chain rule example with a very simple nonlinearity, the exponential function. I don't know if I need to go through this example. It's just an application of the chain rule. We've seen this before. For deep neural nets, they look like this in general. And so let's just start with the final layer. So we're going to start with the loss on the final layer. So we're going to hold all the weights of everything except for the last layer fixed. And then we're going to apply the chain rule backwards from the last layer, because that's how it's going to be applied since we're taking the derivative with respect to the loss. And the way they typically do this the way they typically like to conceptualize this in deep learning is to draw this kind of dependency graph. So this is a graph of the dependencies of how we get to the loss. So we have the target label. The loss is a function of the target label and the output layer of the neural net. The output layer is a function. Is in this case I think the identity is the output of the nonlinear transformation of the previous output layer times the weights of the last layer, and so on and so forth. The reasons why they do this is because neural net architectures can get complicated. This is just a simple feed-forward neural net. And neural net architectures can get complicated, and this type of graph structure allows for ease of software design for complicated neural nets. Is that a question? And so the function basically runs along the black arrow to get to the final output. The derivative for updating the weights, W, run backwards. Right? So that's the chain rule. The chain rule gets applied, invoked, as you walk along this derivative graph to the green node, which requires updating from gradient descent. And basically it's just a multiplication of all of these terms. Each of these terms are computed, holding the other terms fixed, and then we apply them together. And that's called backpropagation. Hopefully nothing here is too mysterious. It's just just a complicated, well, it's messy to write down, but of course if you write it down just as this dependency graph and you write a piece of code that just recursively does this automatically, it's actually not that complicated. But it's complicated, of course, if you write it all by hand. Okay, so now let's go back one more layer. So we'll draw the dependency graph again. We're going to go back one more layer, so to the penultimate layer, and we'll also include the last layer. And now we want to compute the gradient with respect to the second to last layer, the penultimate layer. And by chain rule, we know that it looks like this. We can also draw the dependency graph that looks like this. And those are all the terms that get multiplied together. And one thing that's interesting is that the gradient of the last layer and the gradient of the second to last layer share two terms in common, right? You see the path, the red arrow path, the top diagram and the bottom diagram share two links in common. And so if we compute the gradients in reverse order of the layers, we can actually reuse some of the computation that we've done. So if we have a data structure where that is associated with this dependency graph, and we compute the gradients in reverse topological order in terms of the layers, then we can actually reuse computation as we compute the gradients. Okay, so this is the backpropagation algorithm. Compute the gradients. We store the relevant ones that we expect to be reused, which is everything down that central path. We loop backwards in reverse topological order. We can repeat, and we can reuse the gradients as necessary, keep storing more of it, and so on and so forth. So at every, so we don't have to recompute some of these terms over and over again. If we did, computing the full gradient would scale quadratically with the number of layers. When we do this storing trick, it only scales linearly. And as you can imagine, if these neural nets get kind of complicated, then these types of logic can make computing gradients a lot cheaper than not doing so. After we've done it for all the layers, we compute this vector, which is the directional derivative with respect to every layer. And that full vector is the gradient with respect to the entire parameter of the neural net. And then we do gradient descent. Well, in practice, stochastic gradient descent, but same idea. Okay, just to recap, we have a loss function. We want to minimize this loss function as a function of the weights of the neural net, just like we do in any supervised learning problem where we want to solve it using gradient descent. Because of the complexity of a neural net, we have to be a little bit careful about how we compute the gradients to make sure that we compute them as efficiently as possible. This idea is called backpropagation, which from that community, which is basically just a clever use and storage of the chain rule. And most deep learning software libraries will automatically do this automatically. They would typically, in most of these modern deep learning libraries, specify this layer architecture with these dependencies. And then the backpropagation, the efficient backpropagation is done automatically by the optimization engine that is sitting inside these deep learning libraries. This is a field also known as automatic differentiation. Yes?
I have a question. Like, just like in the big picture way, like how would you go about optimizing like vanilla back like the normal one? Is there like
What do you mean by optimizing it?
Because there's like different optimization, right? Or is it just normal backpropagation, like what you just described? Like
So I'm describing gradient descent right now.
Yeah. is that just what gets used in practice, like this plain version of it?
So there are, right. So there's an optimizer that the most popular optimizer is called ADAM, ADAM. It's adaptive gradient descent with momentum. What that basically does is it has some special tricks for the step size. So normal stochastic gradient descent, you pick a fixed, the step size is chosen in a fairly simple way. But you can imagine where some places I'm going to make the step size bigger, some places make the step size smaller, and ADAM does that. But that's where it differs from normal gradient descent.
So it's just like in those wave updates, not really.
It's in the choice of step size, yeah. So the biggest difference, so all the optimizers actually just do the same. Well, the majority of the popular optimizers do the same thing. They're just doing gradient descent or stochastic gradient descent. All the variability is in how you choose the step size for the majority of the popular optimizers. They like to call themselves different optimizers. I just see them as variants of gradient descent. Any other questions? Okay, so a few comments about implementation. So one of the most attractive things about deep neural networks is that they are so easy to parallelize, right? So it's a bunch of matrix multiplications and pointwise operations, like taking the nonlinearity of each component of your vector. So this is an artificial neuron. We want to actually compute the entire set of activation functions for an entire layer of neurons. It's just a matrix vector multiplication plus a nonlinearity applied to the output vector. We can also do data parallelization, where we can actually apply a single neuron across multiple input examples simultaneously. That's also a matrix vector multiplication. So unit parallelization versus data parallelization, with different choices of architectures and other things, people think about different ways of exploiting these types of parallelism to dramatically speed up neural net training. And in fact, you can speed up neural net training by a lot if you have effective parallelization, a factor of 100 or more. Yes.
Can you use both of those at the same time?
Yes, I think people do. Yeah, funny story about data parallelism. And unit parallelism. Which one is better actually changes from paradigm to paradigm. You might think that one is much better than the other one, and then people come up with a new network, and it turns out that the other version of parallelism is 100 times faster than the first one. You see this come up over and over again as people design new architectures over the years. So one of these might be the flavor of the month right now, but having been around the block a couple times, you can expect that to change depending on the architecture and the data. This is just a simple implementation. You can, of course, there are these giant implementations that people have that sits underneath things like TensorFlow and PyTorch. But for a simple neural net, you could implement it yourself, right? So, this is just the outputs of a layer. You do a dot product of your weight matrix. Each layer is parameterized by a weight matrix and its inputs, which is the output of the previous layer. You do this dot product, and you apply nonlinearity. The simplest one is ReLU, which is just you take the max of the output with 0, and that's how you compute the layer. And that's it. This is a neural net. You just recursively call this thing with a bunch of weights that you've stored. So in the simplest case, this is all you need to do. Okay. So the biggest challenge of deep learning until recently has been the fact that if you have a really, really big neural net, implementing back propagation and all the chain rules can be very complicated, especially as the neural net architecture becomes kind of weird. Again, we're just doing standard feed-forward neural nets right now, just to keep it simple. The deep learning software libraries that are available today do this for you automatically. And that is part of the reason why deep learning has become so popular, is because not only are there powerful function approximators, they're now, relatively speaking, much easier to use. Just build a computation graph, define a loss function like cross entropy on the data, and then it will just run gradient descent or some variant of gradient descent like Adam until the weights converge to something that has high performance with respect to this loss function. Sorry. Any questions? For the homework, we'll be using PyTorch. I'm not going to ask you to implement that problem on a 10-layer neural net by yourself. Okay. Okay, so I'm going to close out the lecture with just kind of survey of like some tips and tricks and some interesting observations about training deep neural nets. A lot of these are, I call them tips and tricks because, understanding how to properly train neural nets is a topic of contemporary research. So even though through, laborious engineering and the brilliance of some very dedicated people, we've gotten deep learning to work enough where they're incredibly useful. A full systematic understanding of when they work, how can improve them is still very elusive, and is the topic of current research, is the topic of the research in my lab, and the topic of research in multiple professors here at Caltech. But in lieu of having a nice scientific understanding of how to properly train neural nets, here are some tips and tricks. Okay, so nonlinearities are essential. Without them, the network collapses to a linear function. So these sigmas are these nonlinearities. They are essential. Without them, it just collapses to a linear function. Just by associated rule of matrix multiplication. Different nonlinearities results in different functions and optimization surfaces. So the choice of nonlinearity makes some of the optimization problems easier or harder, and the choice of nonlinearity, of course, the stretching makes learning certain types of functions easier or harder as a function of number of layers and number of neurons in each layer. Although, of course, in the infinite limit, they are all universal function approximators. Okay, so one of the reasons why neural nets, up until relatively recently, were not so popular, this is a fairly minor reason, but it's still a very relevant reason, is the choice of nonlinearity. So old school linearities look things like sigmoid. So the output of every hidden layer is processed through a sigmoid. This is a monotonic transformation of the raw signed, unnormalized signed distance of the hyperplanes in each of the neurons. Hyperbolic tangent, same thing. The new school nonlinearities, the most common one used these days is the ReLU, which stands for rectified linear unit, and it is just the max. It's just a max operator. You take the max of the signal with 0. So if it goes below 0, you just flatten it out at 0. That's it. There's the leaky ReLU. There's the soft plus. There's the ELU. But I would say the ReLU is by far the most popular one these days. The key qualitative difference is that the old school nonlinearities are saturating, right? They as the raw score go to negative infinity or go to positive infinity, the activation function compresses them to some saturating point. The new school ReLUs are non-saturating in at least one direction. Yes?
So when choosing nonlinear heat functions, is the best way to do it now just kind of veer towards the new school and just try them all out, see what works best?
I would just say just use ReLU.
Okay.
If it's really not working, try some of the other ones.
Okay.
Yes, question?
Why is it like rarely more popular as a zero derivative than negative infinity? Why not just use something like leaky gravity that actually has that derivative? They can both directions go.
If I knew the answer, I would just tell you right now. Let me see. So, I mean, there's no good reason.
Is it just empirical?
Yeah, I mean, I think the value is more efficient to implement. You just compute this max operator, and then things are zeroed out. It makes things more efficient to implement. And I think leaky value, it's not clear when it offers a benefit. In which case, just go with the simpler one. Yeah. If there was some scientific understanding of when leaky value is better than value, then I could tell you when to use leaky value.
Yeah.
Yeah. Question.
If the discontinuity of derivative is not an issue, then why didn't the people before us just didn't use hard threshold?
Why did the people before use sigmoid and hyperbolic tangent?
Yes, instead of hard threshold.
I couldn't tell you why. Things that look obvious now just probably didn't look obvious 30 years ago. I mean, when people invented the internet back in the 90s, we thought that like TikTok would be a thing, right? I mean, it's so obvious to everyone now, right? So I can't really answer this question.
But you can't use a hard threshold.
Yeah, the value is the most popular, and I would certainly recommend it as the default these days. Yes.
Is it possible or advisable to use different activation functions for different layers?
It's possible. When you define your compute graph, you remember I had to define that compute graph, you have this layer, you use whatever nonlinearity you want. Now with most modern, like with TensorFlow or PyTorch, it may be hard to have a mixture of different nonlinearities in the single layer just because of how the software is written.
Yeah, because within a single layer, it doesn't seem like a good idea because then you can't parallelize it.
Yeah, so between layers, yeah, you can just specify weights, number of neurons, what nonlinear you want to use, weights, number of neurons, size of neurons, what nonlinear you want to use. So that's easy to implement in like any of the deep learning packages. Within a single layer, I think it's hard. You may have to open up the API to do that. Okay, so one of the reasons why the old this is actually somewhat debated now, but I'm going to go ahead and say this anyways. One of the reasons why the old school nonlinearities suffered was because of this thing called vanishing gradients. In particular, these saturating nonlinearities impose a very small derivative as soon as you leave this middle region. And so if you apply the chain rule, you're multiplying this small, it's a multiplication of a bunch of derivatives, right? So that means if you have this number that's like 0.1, which is what happens if you're saturating, the derivative, the slope is very small. You have 10 layers, 0.1 to the power of 10 is just this really small number, and so your gradient descent is making super slow progress. The reason why I say this is somewhat debated is that there are now ways of training neural nets where you make sure you stay in that interesting region. So you make sure that the activations stay in that interesting region and not go towards the saturation points so quickly. But of course, if you don't do that, then this is a problem. So, yeah, so I just said all this. Yeah, so if you happen to be in one of those saturated regions, the slope of those regions are very small. Therefore, the chain rule means you're multiplying this really small number. You have 10 layers. This thing just doesn't train. So in the back in the day, like in the 90s, I think the deepest networks they could train are 3 layers. We now have methods that can train 10,000 layers. The value looks like this. The derivative is 1 forever on the positive side and 0 forever on the negative side. So positive region, the value does not saturate. So as long as this neuron is active on some subset of the training data, it will always pass a gradient through. Of course, once a neuron becomes negative, doesn't activate on the entire training data, then it's a dead neuron. Unless the weights down, the weights further below change the representation. So I guess it's a complicated. But typically, in practice, they become dead neurons. But if you initialize your initial weights in some kind of random way, then this will not happen with high probability, and so you should be. Okay, normalization, right? So one of the things that is a problem with RALUs is that, sorry, I'm jumping ahead of myself. So this is normalization. How do we keep, if you have saturating, sorry, I'm jumping ahead of myself. If you have saturating hidden these nonlinearities, try to keep the inputs in the dynamic range of the interesting part of this nonlinearity. So you can normalize activations before applying the nonlinearity. Something looks like this, right? So normalizing is typically something like a shift in scale, also known as whitening. So if you insist on using something like a logistic function for your nonlinearity, you can do something like this. Batch normalization normalizes the layers, each layer's entire activation according to the statistics of the batch. So what does that mean? That means if you're doing, if you have the entire batch's mean activation and the entire batch's standard deviation of the activations, then you normalize across the entire layer. Batch normalization, for reasons that are still not completely understood, was able to significantly speed up training of neural nets. So, we're doing this transformation of each layer's activations while we're doing, stochastic gradient descent. And there's some reasons that people have tried to study that explains why this works. And they've studied both empirically and theoretically things like, it seems to add a little bit more stochasticity, so which perhaps will prevent overfitting, therefore improves generalization. But in reality, I'm not sure people. I think the verdict is still out on what batch normalization is doing. So this is maybe just like a little. I think that this slide, the previous slide, and the next slide is a little bit of a microcosm of the current state of the art and state of research in machine learning. Notice that this batch normalization work was published in 2015, so four and a half years ago. And at that time, they defined a term called internal covariant shift. So changing weights during training results in changing outputs. Input to the next layer changes, making it difficult to learn. So so the internal covariance. So if you think of each layer as so for in statistics, the covariates are the input features. That's the terminology. And so every layer, the input features are the outputs of the previous layer. And then all the layers of the neural net of the weight layers are changing simultaneously. It's causing this shift, which makes it difficult to learn. At least that was the original motivation. So you could analyze this using the histogram of activations. So these are statistics of the input features to the next layer. So what batch norm does is it says, I'm just going to normalize this distribution to look the same every time. But, if you actually, play with the step size, play with the architecture, run different experiments, you can empirically see that, some of the claims or intuitions made in the original batch norm papers don't seem to hold in practice, or at least not all the time. And there's evidence, new evidence suggests that batch norm may be doing something else, such as stabilizing the gradients, smoothing optimization surface, and you can measure these in this way. And then now there's more research, including some from some of my PhD students, suggesting that something else is happening. So this paper was just published a year and a half ago. So this is still indeed a topic of ongoing research, and this is just one aspect of training deep neural nets, just on whether or not to use batch normalization in between the layers. So if you think about all the complexities of training a neural net in terms of all the different pieces you add to just the vanilla standard stochastic gradient descent, including what is the step size, right? There's many papers. I say kind of tongue in cheek, oh, they're all just stochastic gradient descent, playing with the step size, but in fact, entire dissertations are written about what is the proper way to set the step size, because and the choice is very complicated, depending on the number of layers and all that stuff. So it is it's a PhD thesis worthy topic. Yeah. And I have students who work on trying to understand these aspects of deep learning training as well. Okay, so regularization. Deep neural nets are amazingly flexible. Right? So these days they have billions of parameters. And in fact, let's see. Let me just skip through this. Let's talk about, okay, sorry, I got jumping ahead of myself. Sorry about that. So regularization provides overfitting. So it turns out that stochastic, sorry, I'm not used to keynote. Stochastic gradient descent itself appears to provide a form of regularization. So if you train a neural net, at least for small data sets, you can do this. You train a neural net using gradient descent, so you make a gradient update through an entire pass of the data, versus training a neural net using stochastic gradient descent. You force the neural net to use these stochastic gradients. Turns out that stochastic gradient descent seems to have properties that help, as a learning algorithm, seems to have properties that helps the neural net generalize better and overfit less. Because somehow you're injecting more randomness to the neural net, and therefore it causes it to overfit less. There's another method called dropout, which is I randomly deactivate certain units of the neural net during training. So some intuitions similar to random forests going on here, where I backprop when I'm training on a batch of data, and I do this backprop. I randomly force some of the neurons to be zero, and I don't backprop through them. No one exactly understands what dropout is doing, but it was something that was crucial to helping deep learning win a certain class of challenges, machine learning challenges, because it helped it generalize better. Yes?
So I understand how regularization comes into it. I understand that like SGD and virtual could avoid getting stuck at a certain local minimum, but regularization is like shrinking the hypothesis space, correct? So
that's right.
I'm not sure in that sense how SGD is regularization.
That's a great point. Okay. In lecture 3, I went on and on and on about Lagrange multipliers and how regularization is equivalent to having this smaller hypothesis class. And everything I said in that lecture was true. And I think what's happening here is can be related to that. So if SGD is adding noise to the learning, and remember these are non-convex optimization problems, so they can fall into various local optima. So there, I am saying something that is, I do not know if it can be established mathematically or not, so keep that in mind. I'm just saying this purely based on intuition. Perhaps we could prove something together, I don't know. But here's the intuition, but I don't 100% believe it because I haven't seen a proof of it. If SGD is adding enough randomness that I can get into good local optima, then the learning procedure is itself excluding certain neural nets in function class from being learned. So because I have this non-convex optimization landscape, and maybe there's some parts of the local optima that can get good training loss but have terrible test loss. If there was some property from the randomness of SGD that causes those local optima not to be discovered by this optimization procedure, and they get stuck in local optima that generalize better, then SGD as a learning procedure is somehow implicitly excluding certain parts of the function class, and is therefore is a form of regularization. Yes?
Do we have reason to believe that the good local optima are more likely to be found than the bad ones?
So this is actually the topic of a lot of current research, studying how SGD promotes generalization in deep learning. And from the function class perspective, it must be the case that it's finding good local optima, therefore excluding parts of the function class that correspond to bad local optima. I mean, that must be the case. Exactly how that is, like establishing a thorough, complete mathematical connection, is the topic of current research. So people have studied stuff like this for like 2-layer neural nets, but for general neural nets, it's hard to study. Yes, question.
So are you comparing SGD and gradient descent for like the same number of epochs? Or was it SGD?
Epochs, yes, epochs runs through. Okay. In this particular case.
No. I mean, I don't know.
In this particular case, we're just talking about generalization. Like, well, I'm not talking about how fast you learn. I'm talking about the solution you learn, the model you learn. How well does it generalize, and how badly does it overfit?
But isn't like reducing the number of epochs also generalization?
Yes, early stopping. Yeah.
And is it possible that SGD is just sort of a less effective optimization method, so they're running the same epochs?
It's all possible. This is a tips and tricks section of the lecture. I'm just telling you what people have seemed to observe empirically or anecdotally while doing these things. A complete understanding is still quite elusive. Yeah. I mean, yeah. We can train neural nets up to 10,000 layers. I mean, yeah. I mean, the state-of-the-art NVIDIA GPUs have lots and lots and lots of cores. My students, my PhD students, even here at Caltech, where they don't have the same resources as industry, they regularly train 30-layer neural nets easily. Yes, question?
How does the expense change
How does the expense change with the number of layers? A lot. Yeah.
Like does it change linear square?
Oh, does it change linear? I have no idea. I'm sorry. I think that you have to plot it carefully and see if the plots are consistent across different architectures. I've not done that empirical study. I don't know if anyone has. Maybe someone has. So the other thing is initialization. Let's see, I'm showing you 10 minutes. Okay, 15. Okay, so initialization. So if you think about a value, if I initialize the weights at 0, it doesn't learn anything. It's always none of the hidden units will activate because you have the shape of the value nonlinearity, and basically, nothing happens. And so people have thought very carefully about how to initialize the weights of the neural net at the beginning of training. So common strategies include uniform and Gaussian, because you cannot have the weights at exactly 0. Optimization, we have SGD, so we've talked about some of this. We have recent variants. Atom is not in this particular one, but Atom is just another version of this. So, for example, if you can add memory or momentum to the gradient, so you keep going in a certain direction. And so here's just a visualization where SGD goes very slowly, and different versions with momentum converges much faster to the global optimum. And then you have what's called a saddle point on the right. So a non-convex function often has saddle points, where the gradient looks convex in one slice of the space, but it's not a global optimum. And so if you want to escape a saddle point, these momentum terms can help you escape saddle points. So, Atom is the most popular gradient optimizer these days, and it's basically a version of SGD that has a special momentum term. Okay, connectivity. So here I'm visualizing the number of layers. So each circle here is an entire hidden layer. So this is a This is a 7-layer neural net. A very popular type of learning neural net architecture is called a ResNet, a residual net, which basically means that I propagate the output layers of a previous layer, the outputs of a previous layer forward, and then I'm just learning the residual. So this approach was able to scale neural net training from about 20 to 30 layers to about 200 layers by doing this residual connection. And the reason is that if this propagation of information is sometimes very hard. So even with a ReLU, with just by itself straight up, it's hard to propagate more than like 20 or 30 layers. And once you have ResNets, which is the architecture you see at the bottom left, then you can easily go up to about 200 layers. So these are just a few examples of more exotic deep neural net architectures, and now if you have this compute graph, you have to figure out how to efficiently compute the general. We'll go through this a little bit quickly. There's a method that's very popular these days called attention, where you have a part of the architecture that actually masks out part of the data. So there's a part of the neural net architecture that will mask out the data, so and it will only let certain parts of the data through. This is typically very popular for things like sentence processing and image processing. And some of you may have heard of things like GPT-2, released by OpenAI, which is a deep neural net for text modeling. It uses attention extensively inside its architecture. You may have may want to take gradients of non-differentiable operators. So for example, taking gradients of a categorical or some stochastic function where you only get samples, or discontinuities, or just non-analytical operations. For example, if I want to maximize reward in Atari, a video game, in the bottom row, and the agent is a neural net that maps states to actions, and I want to maximize reward, well, this is a non-analytical function. How do I optimize for it? The way you do that is you say, well, I'm not able to analytically compute this function loss function that I'm solving, but I noticed that this loss function is an expected value or an integral over over a smaller over some dependent variable. And so I can approximate this integral by sampling. And don't need to go through the details, it's not important, but these are just different ways of doing that under different conditions. So people have studied how to solve these. How do you differentiate through a loss function that itself is not differentiable? This is what reinforcement learning does all the time. And the observation is that most of these times the loss function is defined as this integral over these terms, and even though the integral doesn't have a closed form analytical solution, you can sample from it. Okay, another thing that people have thought about these days is learning to optimize. Some people call this a form of what's called meta-learning as well. Rather than computing gradient descent through the analytical backprop and chain rule stuff, we can actually say, okay, well, we're going to do gradient descent, but instead of computing the gradients, we're going to do this iterative updating of the model. But instead of the model parameters being updated through some form of gradient descent, we're going to update it through a neural net. Let's say F is a neural net. So it's a neural net that's trained to optimize a neural net. So F is a neural net, and it has learned to compute updates of a bigger neural net so that it can make bigger step sizes, bigger jumps than, let's say, normal gradient descent can do. And then you can train F on a family of learning problems. Let's say I have a family of image classification problems, and I can actually train F to train a neural net for each of those optimization problems, so that in the future, if you have some new image classification problem with a training set, I can use F to train an image classifier on that training set super fast. This is called learning to optimize. It's like a meta-learning approach. Adversarial examples. So these neural nets are super high capacity, which means that if you just perturb the data a little bit, oftentimes it's for whatever reason, it can get the image classification completely wrong. So for example, this is an image of a panda, so the input features are the pixel values. If you add just a little bit of a noise to this neural net, to the inputs of this neural net, and now it's super confident that this image is a given. So these are called adversarial examples. Some other ones where you perturb the image of a stop sign, and the image classification model no longer thinks it's a stop sign. Bayesian neural networks, so we can maintain an uncertainty over the network activations and or weights. So rather than having the weights or the activations be this single point estimate, if you will, of a weight, we maintain this distribution over what the weights can be. And this can be a way to prevent overfitting. Okay, generalization. So I love this plot. Okay, so look at the bottom left plot. It's a training set, and we have the average loss, and the red line is where every data point in this training set was given a random label. So the labels have no meaning whatsoever. And yet, the neural net can learn to fit the noise label perfectly. So clearly there's something weird going on here. Every image, just give it a random label. Dog, cat, bear, car, whatever. And the neural net can learn zero training error. I mean, obviously it doesn't generalize it. So this should give you pause. Okay, one more thing, and I'll just run through this quickly. People have tried to figure out what exactly is actually being learned in between each layers. So obviously this works, and I give you some intuition. I give you an existence proof, or I give you an intuition about the existence of good sequences of layers in the first part of this lecture with that transformations. But it doesn't necessarily mean that stochastic gradient descent will discover things that look like that. Right? It's not guaranteed. Like just because there exists a neural net architecture that has that interpretation doesn't mean that stochastic set will discover that a neural net architecture within the family of neural nets that has that interpretation. So some people have said, okay, well, these types of learning, they tend to lead to layers of representations that, using information theory, maximizes the mutual information between the input and the output while discarding information that is not irrelevant to them. And so neural nets, and from this way of thinking about learning, in deep learning, neural networks learn a sequence of representations that compress the input while preserving the relevant information for predicting the output. And people can estimate this. People can estimate these things empirically by computing the mutual information between every layer and then the output variable using various information theoretic tools. Okay, how much time do I have? Out of time, so I will skip the historical perspective. It's just a little bit of history. The slides are on the course website, so you can read this yourself. It's pretty self-explanatory. And next lecture, we will have an overview of some more advanced neural net architectures beyond FIFO.